All right, guys, let's look at lesson 3, which is the combined gas law. So in lesson 2, we've talked about all of the gas laws separately. So now we're going to combine them all. So the combined gas law can be found in table T in your reference packet. It has pressure, volume, and temperature in it, and it's P times V over T equals P times V over T. You think about these 1s and 2s as the initial conditions and final conditions. Two main things though, your pressure is either going to be in kilopascals or ATM. Your volume is either going to be in liters, milliliters, or centimeters cubed. And your temperature always has to be in degrees Kelvin. So how do you use the combined gas law? The first thing you got to do is you got to make sure all of your temperatures are in Kelvin. Make sure you use the same unit for both volume and both pressures. And if one variable remains the same, then you can cancel it out of your equation. So let's just remember a little bit that we've talked about in the past. So when you're converting units of pressure, so say for example, if you're going from kilopascals to ATM, you're going to set up a proportion like table A has. So what is the pressure in kilopascals of 0.92 ATM? So we know from table A that 1 ATM is equal to 101.3 kPa, and we're looking for how much 92 ATM is, and that's going to equal how much kPa we have. So what we're going to do is we are going to cross multiply and solve. So it's going to be 0.92 times 101.3. So our answer is going to be 93.2 kilopascals. The other thing we need to remember how to convert is temperatures. We talked about this in our last unit when we talked about heat, but let's look at this again. So Kelvin is equal to your degree Celsius temperature plus 273. So, for example, what is 33.7 degrees Celsius equal to in Kelvin? So we're going to take 33.7, we're going to add it to 273, and we're going to get 306.7 Kelvin. Awesome. So now you guys are ready to solve any of these problems. So let's look at this example. A gas in a rigid container has a pressure of 3.5 atmospheres at 200 Kelvin. What is the pressure at 273 degrees Kelvin? Well, our temperatures are in Kelvin already, so we don't need to do any converting. So let's plug in what we have for our variables into the different equations. So we know that it has a pressure of 3.5 ATM at 200 Kelvin. So those are going to be our P1 and our T1. We don't know a volume though. And we don't know what our pressure is at the new temperature, which is 273 degrees, and we don't have a volume. The good thing about this is that if you look in the first part of this question, it says it's in a rigid container, which means that its volume is not going to change. So we can get rid of the volume out of this equation right away, and it's going to just simply be equal to 3.5 ATM over 200 Kelvin is going to be equal to our new pressure, which we're going to calculate, divided by 273. So let's rearrange and solve for P2. To solve for P2, what I would do is multiply each side by 273, and I would get this. So in our calculator, we're going to type 273 times 3.5 divided by 200 and get our new pressure, which is 4.8. And the units of our pressure that was in our problem was atmospheres, so that means that our answer has to be in atmospheres as well. Pretty easy. Let's look at example 2. Example 2 says a 32.9 liter sample of a gas at constant pressure increases in temperature from 25 degrees Celsius to 45 degrees Celsius. Should the volume increase or decrease? Calculate the new volume. Well, first of all, we learned back in the last lesson that Charles' law has a direct relationship between volume and temperature. So if the volume should increase as the temperature increases. Since our temperature increases here, our volume should get bigger. So let's double check that with some calculations. Before we get plugged into our P1V1 over T1 equals P2V2 over T2 equation though, we need to calculate what these temperatures are in degrees Kelvin. So let's plug in our formula. So Kelvin equals degrees Celsius plus 273. So let's do the first temperature. That's going to be our T1. And the second temperature, which is going to be our T2. So now we're going to plug into our equation. We don't know what our pressure is, but we know the initial volume is 32.9 liters and the initial temperature is 298 Kelvin. And like I said, we don't know what our new pressure is going to be but what our new volume is going to be, but that's what we're solving for. and our temperature increased to 318 Kelvin. In the problem, it says that constant pressure. So we're at a constant pressure. So guess what we can get rid of? We can get rid of our P's in our equation because we don't have it. It's not changing. It's going to be constant. So then our equation is going to end up looking like this. To solve for V2, what we're going to do is we're going to multiply each side of the equation by 318. On the right side, it's going to cancel. On the left side, it's going to be 318 times 32.9 divided by 298. When we plug that into our calculator, we're going to type 318 times 32.9, and we're going to divide that product by 298. And when we do that, we get 31.5 liters. Awesome. So try this practice problem. Pause the video and unpause when you're ready. Alright guys, welcome back. So the first thing we're going to do, since our temperatures are in degrees Celsius, is we are going to convert them to Kelvin. So let's do that first. Remember, each temperature plus 273 is how you're going to convert them to Kelvin. And now let's plug in what we have into our equation. 101.3 kilopascals is standard pressure. It's in table A, so you can get that right off of table A in your reference packet and plug that in. 45 milliliters is our initial volume, and our initial temperature is going to be that 293 Kelvin. Now our final conditions are going to be 107.9 kilopascals for our pressure, and our new temperature is going to be 323 Kelvin. So how we're going to solve for V2 is we're going to multiply each side by 323 and divide by 107.9. So our new equation, once we do that, is going to look like this. So now when we type this into our calculator, we're going to type in 101.3 times 323 times 45 and then hit enter and get an answer. Then you're going to divide that answer by, in parentheses, 293 times 107.9 end parentheses. And if you do that correctly, you should end up with 46.5 milliliters, which is good, and it's accurate because our temperature increased, so our volume should increase a little as well. So let's look at this second practice. A total pressure inside a 2-liter container at 28 degrees Celsius is 1.03 atmospheres. If the temperature is lowered to 0 degrees Celsius while the volume remains the same, what is the new pressure inside the cylinder? Pause the video and unpause when you're ready. Great, well, welcome back. What did you come up with? You should have first converted all of your temperatures to degrees Kelvin. Then what you should have done is plugged in. Our initial pressure is 1.03 atm, and it's a 2-liter container, and that temperature is 301 Kelvin. Our second pressure is what we're solving for. Our volume didn't change, and then our second temperature is 273 degrees Kelvin. Since our volumes are not going to change, we can just get rid of those and cancel those out, and so our equation is going to boil down to just this. So then what we're going to do is we're going to multiply each side by 273, and we get this. Plug into our calculator, and you should get 0.934 atmospheres as your final pressure. All right, so we've done a lot of we've done 2 practice problems, we've done 2 example problems, so let's try this, check your understanding. This is the first thing that we're going to go over tomorrow in class. Have a good night.